All right. What? Oh wow, incredible. Reflexes. Good job, Battlestorm. Oh, just a human guy. That's really sad. It's really sad. I bet you Battlestorm has like fancy internet. I bet Battlestorm just has fancy internet. And oh, what? Oh wow. That's maybe, oh, but maybe just a human guy. But maybe just a human guy doesn't have good internet. That could happen. There are many scenarios here, folks. Really. Kappa? Yeah, I mean I have to teach my second class, Kappa. I mean that's how it works. That's how time works, Kappa. Time goes like that. Forwards. Hello, Xiao. Hello, everybody. All three of you. Welcome. Come on in, have a seat. I want to run a poll. I'm going to ask the class a question. Oh man, that sucks, dude. That sucks, Batman. Oh, Toaster, hopefully it'll be better this time. I'll try, I'll try my best. I'm not sure I have any magic powers or anything, but I'll try to make it understandable. Oh, that's great, Kappa. We need more students who are into it, like you. I feel like that spirit of chewing material is a rare thing. Okay. Kevin does chemistry. I duly noted. Duly noted, Kevin. Your input is much appreciated. Oh, thanks. Oh, let me. Thanks, Kevin. Gee, thanks. Gee. Jeez, thanks. Oh, Toaster. Yeah, that's true. Kappa is one of those. That's true. That's true. Shame on Kappa for wanting to understand things deeply. That sucks. That's a bad quality for everybody to have. It's bad. It's bad to want to understand the universe deeply. That's bad. I agree. Okay. Okay, let's go, folks. Let's go. Let's get started here. With some good background music. Alright, students, there's a poll going. The issue is, do you want me to kick the Wednesday assigned homework to next Saturday and double up the Saturday load? Or do you want to keep it separate as it is right now? I need to know that. Because if you want Wednesday, then I think I should probably hold a short office hour stream on Wednesday for you. If you don't, then we can put it all on Fridays to keep the Friday schedule office hours. But I need to know. So go ahead and vote, students, in the poll on the top of your chat. Okay. Okay. Yeah. Right, Toaster. Yeah. Okay. All right, so I guess I'll start the material. Students just trickle on in. Probably just barely waking up and stuff, so just go ahead and, you know, freshen up and come in. What is the topic today? Well, we're in the series part of the course. Okay. What I'm going to talk about today is a particular collection of examples called the geometric series. And the sort of overall situation, overall sitch. All right, let me draw a picture of the overall situation. This is the universe of all conceivable series. What does a series mean again? Infinite addition problem. You take a sequence, put plus signs between them, and say, do this infinite addition problem. Now, what does that mean? Does it actually yield a finite result at the end of the day, or it doesn't? We will talk about that right here, right now, soon. Okay. But imagine all such math problems. They form a big universe, all series. And which series will we understand? Will we be able to understand perfectly? Let me show you. I don't know if you can see that, but this blue dot, these will be the series problems that we can actually do. Okay? It's gonna be bigger than you think at first. Okay, slightly bigger than that dot. Slightly bigger. Those are the ones where we'll actually be able to establish whether it converges or not. But we won't be able to actually find the total sum. All right, necessarily. But look, there's all these others that humanity is too stupid. All right? And so that's the context. So why geometric series? Because they're one particular class of examples that we have perfect clarity on. So let's go learn about them in that spirit. Let's learn what we can, folks. Awesome. Remember, folks, there's an office hours today at 6. Before it, I will be doing my algebra office hours. It's not your grandmother's algebra. It's a little bit different. But then I will try to move to calculus at 6. All right, good. What is a geometric series? Let me start with that real fast. Real fast. Let's go. What is a geometric series? And then we'll look at the frog example. And then we'll look at Archimedes' original example, 4 billion years ago. And then we'll transition to how to understand all the examples of geometric series. Let's go. Everyone get up, start clapping in excitement. 1. What is a geometric series? It is any series which has the following form. Oh, thank you. Yeah. You start with a number called the, let's call this the first term. Then you take that number and you multiply it by another number called the common ratio. And then you take that second term, multiply it again by the common ratio. Incredible. What a pattern. R times R. And then you do it again. And you do it again. In other words, the terms of the series, which means term means individual things you're adding up. The terms of the series, the adjacent terms are obtained by multiplying by one fixed number called the common ratio between the two terms. You see, to go from here to here, you multiply by R. To go from here to here, you multiply by R, and then you add them all up, dot, 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 forever. Any series that fits into this mold is what we call a geometric series. And when you look at one, the first number you start with in your addition problem is called the first term. That makes sense. And the ratio that's being multiplied is called the common ratio. And we call it R. All right? So let's look at our frog example. Frog example. The frog example was green. Is it geometric? Yes. Look, if you let A equal 1, and if you let R equals 1/2, then yeah, the first term is 1, and then the second term is R times that, the third term is R times that, and R times that, and then R times that. It's true. It's true. 1/2, 1/4, 1/8. They're all just multiplication by one fixed number from one to the next. Beautiful. Beautiful. Okay. Okay, so what? Oh, you want the frog? Okay, you want the frog. Okay, this helps you. This is helping you learn. Okay, so what though? How do I know that this series actually yields a finite number at the end of adding them all up? How do you even do something like that? What kind of infinite processor do you have to have in order to do this kind of math? We're gonna learn. We're gonna learn this juggling of infinity. Okay, so I'm gonna analyze the frog example in a beautiful way. Let's do this addition problem. And what am I actually gonna do? I'm gonna do only this part, the golden part. Yeah, I'm gonna do this one. And then at the end, we're gonna add 1. Sensible. All right, but how do you do this one? How do you do this infinite problem? All right, notice it's still a geometric series. It has a different first term. Common ratio is 1/2. Blah, 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 blah. By the way, common ratios can be negative numbers too. I didn't say anything about R being positive or negative. More on that later. Here we go. What we draw is the golden circle. Why is it golden? because that's the color that my pencil's on right now. Now, this circle, pretend we know something about it. Pretend its area is 1. Okay, pretend this circle has area 1. Awesome. What we're gonna do first, cut the circle in half. Half. Isn't that 1/2? Isn't that area 1/2 right there? I think so. I think it is. Okay. Next, take the rest and cut it in half. Here's your slogan for this beautiful story. Take the rest, cut it in half. Okay? So every time it happens, I hope you're in a public place in the library. I want you to yell it. Take the rest and cut it in half. Every time it happens, okay? Right here. Take the rest of it and cut that in half. Yell it. Scream it. Wait, I switched colors. Okay. Well, isn't this 1/4? That's 1/4 of the pie. Take the rest. Take the half and cut it in rest. Yeah. Math Mama. Math Mama got it. Math Mama's getting this. Take the rest of it, cut it in half. Isn't that 1/8? Isn't that 1/8 of the pie? I think so. Take the rest of it, cut it in half. Take the rest of it, cut it in half. Now, think about this. Think about this carefully. If you do this forever, how much pizza is left? Okay, Math Mama, yeah, we got it. We got it? Okay, yes, you can stop. You can, yeah, okay. If you do it forever, how much pizza is left? You know what, folks? I will give you whatever's left after this cut. Take the rest and cut it in half procedure. After it, like forever. Okay, afterwards. Whatever's left, you get that slice. Flush thrown, a microscopic amount. But hey, flush thrown, does that microscopic amount have any thickness? I think no, because take the rest and cut it in half. In fact, there can't be any actual thickness left at the end of, there's no wedge. There's no amount left at the end. Okay, awesome. 0. So, flipping this the other way, the total area is all of the slices added together. All of the slices, when added together, converged. They conspired towards the whole. The sum of the parts converged to the whole. Not at any one finite stage, but forever. At the end of the day, it converged to the whole thing. We get this remarkable conclusion. Amazing. And therefore, That's why. And so, if you do 1 plus 1/2 plus a 4th plus an 8th plus a 16th, this equals the total amount that the frog hopped. Equals 2. As promised.
Wow. 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 Wow.
Educational.
Wow.
Okay. With like great effort and super cleverness using the golden circle, I was just barely able to analyze one geometric series. That's really bad pace, folks. Okay, now I'm gonna do one that's actually historical and not based on frogs, okay? This one is in the realm of biology and science, right? This is a scientific example that I just showed you involving like frogs and stuff. The second one is more in line of history class. All right, so let's do history class now. To show you that math is used everywhere, you know? So history class. History. It's said that Newton or Leibniz, whatever, they're the first person who sort of invented calculus and understood the role of limits and infinity and so on. It's completely garbage, folks. There were some ancient geniuses who definitely understood the subtleties of infinity. They definitely understood that it's possible to do an infinite procedure which converges and yields a finite amount at the end. They understood this general principle. And the person who first understood it for sure was some person named Archimedes. All right? Some genius. All right? It was like 2 billion years ago. All right, so this person, Archimedes, Greek, he wrote a letter to his friend. He wrote a letter. There's some friend. I don't think, whatever, some friend. And is like, oh, hi, hello. I heard about so-and-so passing. I'm so sad, blah, blah, blah. Okay, yeah, like chit-chat. It's hilarious. You look at the end of that letter, Archimedes is like, hey, by the way, friend, I just discovered something rather incredible just now. And I discovered that you can add up infinitely many numbers and get a finite number in an interesting way. I discovered that if you take 1/4 plus 1/16 plus 1/64 plus 1/6 plus ... If you add up these, he didn't have sigma notation at the time, so we'll have to practice that. But if you add up these, you get 1/3. Add them all up. Okay, what I want you to focus on here, class, this is a geometric series. It's A is 1/4. And its common ratio is that's confusing. Is 1/4. Okay? Just look at that. Times 1/4, times 1/4, times. But Archimedes just threw this in there at the end. Like, hey, by the way, friend, I can add infinitely many numbers now. Can you? No? Okay. Well, that's good. Maybe that's why no one remembered you. I don't know. Just saying. Okay. So that's That's the original example of a geometric series, recorded history. Okay? And now I'm going to explain to you why we kept calling such a series geometric. It's the explanation of the word geometric. All right. I already showed you the golden circle example, so that should convince you. But I'll show you the original historical method. Archimedes argued as follows. Start with a golden square. How did that become a vector? Wait, is this a square? Is this a square? That's a rectangle? Oh my God. Is that a square? Thank you. Thank you for that emote. Thank you. Perfectly positioned. Okay. So this is a golden square. It has area equals 1, pretend. Okay? Golden square. Oh, thank you. Yeah. Thumbs up. Thanks. Okay. Archimedes. Okay. Okay, I don't know what the slogan is for this one. I don't know what it is. It's long and complicated. It's break it up in break it up into 4 and then circle color one of them and then do it again. Let me just play. Let me do it. Let me doodle. So, step 1: break it up into 4. Boom. Color that one. Color the. Oh, this is the one. This is how it goes. This is how it goes. I remember now. Break it up into 4. And then color the one in the ceiling closest to the left. Just repeat that loudly in your library at OSU. Got it? Okay, I just did it. I broke it up into the 4th. I colored the top left. Continue. Break this up into 4. And color the top left. Keep going. Oh my God. Oh my God. You get a bunch of boxes on the top of the room, and they go like staircase. Okay? Staircase. Okay. Archimedes says the total area in the top boxes is what I'm after. In red. It's 1/4 plus a 16th plus a 64th plus, because each time I took 1/4 of this, and then I took 1/4 of that piece, and 1/4, and 1/4, and 1/4, etc. Okay? All right. Then he said, do the whole thing again, but start at the blue square. That's a 1/4. And then that is a 16th. And then that part is a 64th, etc. Total blue area. Same. And then he said, okay, take the purple. So this math problem appears 3 times in this square. So the total area which means each of these individually is 1/3. Archimedes was a genius, obviously. This was 2 billion years ago, before the Earth even existed. Okay? So just think about that. You're complaining? This place, Earth wasn't even around, and Archimedes was doing all this. Okay? So we're just learning this stuff. This person had to discover it. Think about how hard that is. Okay, I see a lot of people. Here's your twisted cubic Boole machine. Here you go. It's a little curve here. Battling Storm is teacher's pet. Okay, great. Okay. Juggle. I'll juggle later, LD Hacker. Okay. All right. So, now, class. Oh, Kappa asks a great question. How do you actually prove that it's 1/3? Such issues were not as pressing to the ancients 2 billion years ago. I think it's quite obvious using the geometry, just intuitively, that you exhaust the entire square in this process. And so you do get 1/3 in this procedure. Okay. Awesome. You exhaust the whole thing. That's the proof. All right. Proof by exhaustion. All right. So, in total. Let's just recap. We now understand 2 geometric series. But I promised you, we will eventually know how to write down the answers to all of the geometric series. Okay, so that is what I'll move to now. Smash Time Fools understands the technique. Yes, you make the problem very tired. That is the method of exhaustion that Archimedes pioneered. That's right. He just kept the frog bouncing more and more until it got exhausted. That's his method. You're right, Smash Time Fools. That's you. Well put. Well put. Okay. So we can understand every geometric series in the world, folks. All right, so for me to, let me state the total summary, okay? Or maybe you want an example first. Let me show you an example first. Let me show you an example. Dumb examples. Dumb examples. Here's one. 1 plus 1 plus... You know what? Here. 4 plus 4 plus 4 plus 4 plus 4 plus 4. Folks, this series does not converge. I haven't told you what convergence means yet. It means add up the first couple. Write that down. Then add one more. Write the result. Then add one more. Write the result. This list of partial sums, is it getting to some finite destination or not? Does its limit exist? No. This will just increase without bound. Okay, folks, this thing diverges. But technically, it's a geometric series because there's a common ratio of 1 here. Okay, fine. Here's a dumb example. I don't know, 1/2. 1, 2, 4, 8. This is also geometric. Common ratio is 2. This is common ratio 1. Okay? Yeah. This is dumb. A equals 1, R equals -1 is the most fun geometric series. Okay, we'll talk about that one. Okay, one day. Okay, so this is also geometric, folks. Okay, this is R equals 2. Okay, this obviously diverges. Like the numbers are just getting bigger and bigger without bound when you're adding them. We're adding all of these up, right? There's no hope for conspiring towards a particular value. Convergence. There's no hope. All right, so this thing diverges. All right, so now I'm going to tell you the general situation for all geometric series. I'm going to tell you it first, and then I'm just going to explain what goes into establishing this. Grand general situation. There are two situations. Okay, so let's write our geometric series. Okay, two situations. If the common ratio, just the size of it, if the common ratio is small, then the series converges. And not only does it conspire towards a one particular finite end summation, we can tell you exactly what that number is. It's given by the handy dandy formula. A divided by 1 minus R. If, on the other hand, your common ratio in size is big, like R equals 1, R equals 2, R equals 1.009, R equals -2. We got to think about that later, folks, later. We'll do negative numbers in a second here. If you got a big R, then the series diverges. Okay, that's it. That's the end of the story. It's the end result of this addition problem is not one particular finite number. That's the situation. All right, circle this and put this in your note card right now. This is what we'll at the end of the day use 4 trillion times. Okay, the grand general situation regarding geometric series. Okay, so I'm going to explain. I'm going to explain this statement now. But first, in order to explain that, I need to tell you what it means for a series to converge. By golly. What does converge even mean? What a bad teacher. You didn't tell me you didn't give me the exact definition, and you just dove right in and started drawing shapes? Come on. I demand perfect rigor from the beginning. I'm a robot. Okay, I'll tell you what it means. Ready? Get a fresh note card. I'm going to tell you what we mean when we say a series converges. Suppose A1 plus A2 plus A3 plus A4 plus ... written in compact notation This is compact. We'll practice compact notation on Monday for sure, folks. Suppose this is a series. Okay, suppose you got a series. Okay. We say it converges if, and it's a definition, so if and only if the following procedure works. Following simple-minded procedure works. Okay? I want you to take a just big S, simple-minded. So step 1, write what's called the partial sums of this sequence down. Steven! Now you're gonna need a big, huge note card for this step. S1, sum number 1, partial sum number 1 is add up the first one in this addition problem. Okay, that's just A1. Write that down, circle that. S2, partial sum number 2 is write up the first 2 added up. Okay? Literally go one at a time. Circle your incremental answers. S3, add up the first 3. Make the list of partial sums. S sub capital N is add the first n of them, folks. Make this list. How big is this list? This is an infinite list. It's a sequence. From Monday, it's a sequence. You get a sequence. A sequence of partial sums. So that's the first step. Write out the sequence of partial sums. This might take you a while, folks. Right now, Step 2, simple. Take the limit of this sequence. Look at. This is it's similar to when does an improper integral converge? It's got the same flavor. It says, make this list of your best attempts. First, add the first 2, then this first 3, and then add the first 4, and then circle that. Add the first 10, circle that. 11. Make a huge list, a sequence of attempts. And then you look at the limit as the attempt number goes to infinity, and you ask, does it exist? If exists, that's what original series converging means. If the sequence of partial sums exists, that's what we mean by the original series converging. If not, then the sum diverges. Okay? It's actually simple-minded, this definition. What this definition is saying in words is, what do I mean by an infinite addition problem working out, converging? I mean, go until you can't. Step 100. Circle the answer. Then your child will inherit the series. They'll go and they'll do up until 200. Like, they'll do 100, 101, they'll do 102, and then they'll look at what happened at 103. Summations. Then they'll die at some age. Then their children will go and do it. The series converges if the family's answers are all limiting towards one particular number. That's simple-minded. That's exactly what you think of when you think of an infinite addition problem conspiring towards a particular value. It means that if you try your best and then better, the net totals, the running totals, are converging towards some particular value. The limit of partial sums is getting somewhere, is something. The partial sums are getting somewhere. Now you know what convergence means. So next, on Monday, I will demonstrate why a plus ar squared plus converges whenever the number r is less than 1. I'll tell you why that's true. And then, as a byproduct, we'll see why the formula for this number, the handy-dandy formula, is true. So I'll settle this on Monday. I'll show you how to see this using the definition of convergence. We will actually write down the partial sums carefully with great precision. Then we will compute this limit. Well, no, we'll investigate whether the limit exists or not. And we will say it does if r is a small number. And if r is a big number, it won't. Awesome. Wonderful job today, guys. Today was a difficult class. Let me see what the class chose in the poll. Let's see the results. No, don't double up. Don't double up. You want it Wednesday. Okay. So we will stick to our current schedule, and I would expect a small office hours on Wednesday for the first series homework that's due on Wednesday. All right, so that's our plan. We'll have I'll put in office hours on Wednesday and on Friday. I will work double just for you. Okay, class, that's what you chose. That's what we'll do. Okay. Awesome. Okay. I am sweating. Good job, class. Geometric series. Wonderful history, wonderful biology behind it. Just wonderful overall beautiful ability to juggle this type of infinite addition problem. And we will then grow outwards our ability to calculate or analyze from the geometric series simple examples. Okay, awesome. Let's go look at this thing. Oh, thank you. Oh, Gath. Wonderful. Gath is a great luminary. Gath has an insanely in-depth organic chemistry class going right now. Very, very detailed. They're in the thick of it. I tried to watch, and it's very complicated. Lots of visualization going on. Very difficult. But Gath has these cool props that she helps the students learn with. And word on the street is she made them herself. That's incredible. I'm just, that's so impressive. All right. Let's see what happened in the chat. It's always just really bad. Okay, Anonymous Cowboy says, exam question. Why was Archimedes so sus? Sus is one of the worst words I've ever just... Okay. Can you do the one where 1 + 2 + 3? You mean the one that's just made for pop science magazines and is just false? Yeah, that one. Yeah. Okay. It's funny because people take that one and they get the wrong message from it because the people that just put it out there are like these pop science people. You know? Like, dude, no, that's not the content. The content is not that math is broken. Content is that certain formulas fail to work after a particular domain. In fact, we will see this. Actually, Kevin, we will do a different version of that pop science garbage. Kevin, we're gonna do a different version. Here's the one we're gonna do, Kevin. Students, look away. Students, look away. Look away, students. Look away, students. We will do a different version. Kevin, we'll do this. And then put this on YouTube. 1 + 2. Okay, look at, put this on YouTube, okay, Kevin? You'll get like hundreds of views. You'll get all kinds, okay? Big old thing. Oh, yeah. And then you can write an article saying, yeah, look at this. This is some really deep stuff. Deep. No. There are certain rules where certain formulas are only applicable in a certain range. If you then use that same formula beyond its range, you will get garbage. And math already told you that you'd get garbage. But you didn't pay attention to the asterisks in that formula. Kevin, go and write this on YouTube. Go write it. Just write it right on YouTube. You'll see. Wow, I learned. Some randos on the street will be like, mathematicians, they do some weird stuff. Can't trust them. It's all fake. 1 + 2 + 4 + 8, what? Becomes -1? Come on. It's all just lies. They're not prepared to see it. Yeah? But my class will be prepared. We will learn how to combat the QAnon. We will use the power of Shungite against the QAnon people. Against the people who say this garbage. Against the people who do this. Wait for it. 1 + 2 + 4 + 8. Wait a second. It's -1? No! No, it's not. Okay. Juggle, recorder. Okay, juggling and recorder. At the same time? I don't know if I can do that. I'll try. 2 for 1. Students, review the definition of a geometric series. Write down a couple, your favorites. Review the story of the frog and Archimedes. And then try to parse the greatness of the grand situation conspiracy that I wrote on the board. All right, got 2 for 1. So that's for both of you, LD Hacker and Just a Human Guy. Package deal, special offer. Okay. All right. Okay, folks. So who's on the credits today? Credits. Let's wind down. Wind down. Okay. Okay, so for this person here, Danny, to get in the credits, they just quickly followed right now. Did I get that right? That doesn't count. Okay, fine. You know what? Okay, Danny. Welcome. Yes. Okay. Good. You made it in the credits. Good job. All right, but who really made it? Who really made it, folks? Who made it? Well, in the beginning, there was Battling Storm. Battling Storm sat in the front row today. Social distance, though. Teacher's pet. Like instant. And stole it from Just a Human. Alright, so I'll just put Just a Human as sort of consolation type prize. Like, you know. Who else was out there? Kappa. Kappa is very smart. Is very smart. I like Kappa. Okay, next. Who else was there? I didn't really pay attention to the now do it all again in binary. Pizza party. Oh, wait. All the people that yelled, take the half and cut it in rest. Wait. No, take the rest and cut it in half. Math Mama. Kevin? Does Kevin deserve? Okay. Math Mama, Kevin. Flushed. Go Pokes, I suppose. Who else was there? Flush Throne. Who else did that? Hey, Open Set is here? Yo, Open Set. Hey, everyone. Hey, dude, our shout out game sucks. Hey, Open Set. Go check out Open Set. Everyone, all your math questions, go ask Open Set. They'll play beautiful music while answering it and while looking at a microscope, all at the same time. It's an incredible place. Very, very awesome. Highly recommend. Okay, Open Set. Okay. Who else made it in here? Who are we rating? So you're trying to push me out, Anonymous Cowboy? So Anonymous Cowboy is asking, okay, so get to it. Who are we raiding? Trying to push me out. So you're not in the credits, right? That's what happened. Of course, there's the perma credits. All right. Cool. You made it. You made it, Kevin. Oh wait, new person Shao. All right. Okay, done. You just followed 4 minutes ago. No, you didn't make it. You didn't make it. The cutoff. There's a cutoff. All right, folks, let's do this. What happened today? Not this. This did not happen. That don't read that. Don't read that either. Okay. Okay, don't read that either. Okay, we'll start here. Credits. Folks, we had a good day today. Today was about geometric series. First lecture. I will finish it up with the grand conclusion, which states that we know how to parse every single geometric series, no problem, on Monday. Okay. We gave 2 examples. Beautiful. One was involved the frog, and the other involved Archimedes and his buddy. And we didn't do much outside of that. Because not very good at teaching. So that's that. Let's see who to raid. Okay, there's XQC, there's Healthy Gamer, there's Kit Boga, jeez, Hikaru. Huh. These people are too small for my tastes. You know, I don't raid down. I only raid upward. So let's actually, the frog will be back. The red frog will be back. The divergent frog, it's gonna be back. All right. Actually, both frogs will be back. Don't worry. Oh yeah, office hours. Office hours at 6 for the calculus people. Okay, who's on? Is Melko on? No. Is Peter on? Professor Peter? No. Is oh yeah, right. Right. You want Booyah? You guys want to learn how to make money? All right, let's go learn how to make money. Go show them how geometric series work. Okay? Spread the love, spread the fascination, spread Archimedes' legacy throughout Booyah's stream. Okay? Go do that. Start the raid. Oh wait, you want... Okay, no, I'm not gonna switch. Okay, I said Booyah, here you go, Booyah. You get Booyah now, folks. Go say hi, go earn tons of cash. See you later. Wait, what? Not offline, is he?